So we're going to go through the whole triple constructive proof or constructive rules one by one once again. And this time, instead of actually providing an encoding for a Hoare triple, I'm going to constructively specify what Hoare triples are valid and what Hoare triples can be constructed based on certain properties. And this is going to be based on inference rules. So to understand what I mean, let's look at this first Hoare triple, Hoare logic rule, and these are the rules of the so-called Hoare logic. This is the assignment statement x colon equals e, and if this is my program, then this Hoare triple holds. What is this Hoare triple? Well, this time instead of saying arbitrary p and arbitrary q and then trying to provide a corresponding logical encoding, I'm actually doing a constructive proof. So I'm saying that for any p and any assignment, this Hoare triple holds. And what is this Hoare triple? The precondition is p, where x has been replaced with, substituted with e, x colon equals e, p. So notice that this is a constructive way of specifying what Hoare triple holds. So I'm saying that this Hoare triple holds for any assignment and any p. Notice that earlier our kind of way of specifying this property was something like this. We would say p x colon equals e q, and this is equivalent to saying that p implies q such that x has been replaced with e. But this time I'm not I'm not using this. I'm actually using this way of specifying what Hoare triples hold, and I'm saying that for any p this holds. So for example, if so I'm going to show you an example in the next slide. But the difference between this way of specifying what a Hoare triple means and this way of specifying what a Hoare triple means is that this is a constructive way, or I'm saying that this is, here is a way for any p and for any assignment, this Hoare triple holds. Here I was saying that given a Hoare triple, what does it mean? But that's more like trying to understand what a Hoare triple means. This kind of specification is basically a semantic meaning, giving a semantic meaning to a Hoare triple. Here I'm saying, this is a Hoare triple that definitely holds. And that's why I call it constructive. So let's, before I look at an example, let me give you another composition rule, another rule for Hoare logic, which is again a constructive rule. I'm saying that if for some statement or some program C1, P C1 R holds, and for some other statement C2, R C Q holds for some P R and Q, then I can say that P C1 composed with C2 Q holds. And this is our composition rule. And we have been seeing this rule, we've been applying this rule implicitly all along. This time I'm basically showing you a constructive rule which basically says the same thing. So once again, if P C1 R holds and R C2 Q holds, then P C1 semicolon C2 Q holds, where C1 semicolon C2 represents the composition or the sequencing of the two programs. And this is also called the composition rule. So let's look at an example. Let's say this is my program. It is made up of two assignments. The first assignment is x colon equals 0, and the second assignment is x colon equals x plus 1. And I want to prove this Hoare triple, which is true as a precondition. A true precondition means that there is really no constraint. Basically, it's the weakest possible precondition that you can have, or weakest possible assertion that you can have. And the post condition is x equals 1. Now it's easy to see that this Hoare triple are actually true, but how do we kind of show that this can be constructed from the two rules that I showed you in the previous slide? So this time I'm not going to basically show an encoding of this Hoare triple. I'm going to try to construct this Hoare triple from the two rules that I've shown you in my previous slide, which is the assignment axiom and the composition rule. So the first thing I'm going to do is I'm going to use the first rule, the assignment axiom rule, across the second statement. Let's say I could have chosen the first statement also, but I guess it's easy, because the assignment axiom says for any p and for any assignment, I know what Hoare triple holds for that assignment. I know the P here, I just need to basically figure out what needs to come here. And so when I use the assignment axiom for the second statement is x colon equals x plus 1. The post condition that I require is x equals 1. So both these things are coming straight away from here. And now the assignment axiom says that the Hoare triple holds so this is basically, this forms my P in the assignment axiom, and this forms my C, and what goes before it is basically P where x has been replaced with E, right? And this C is basically nothing but x colon equals E. So E is nothing but x plus 1, and so here P is x equals 1, and x colon equals E is x colon equals x plus 1. And so this Hoare triple can be constructed just using the assignment axiom that I showed you on the previous slide. Now if I kind of just simplify this, x equals 1 where x has been replaced with x plus 1 just becomes x plus 1 equals 1, because after I substitute x for x plus 1, I substitute x by x plus 1, then I get x plus 1 equals 1, and that basically means x equals 0. Alright, so that's basically x equals 0, and so from the assignment axiom I know that I've been able to construct a Hoare triple which says x equals 0, x colon equals x plus 1, x equals 1. Precondition, program, post condition. Now once I have the precondition of x colon equals x plus 1, I can kind of say, okay, let's say that this was the post condition of the first statement. Then what is the Hoare triple that holds for the first statement? And once again, I'm going to apply the assignment axiom and say, okay, x equals 0 comes here. So that's coming from here, right? So this is coming from here. And then I say, okay, x colon equals 0. And from the assignment axiom, I say, so this is, in this case now, this is my P, this is my x colon equals E. And so this is P, and this is the substitution x colon equals E. And so what is P? P is x equals 0. What is the substitution I want? That is x colon equals 0. So x equals 0 substituted with, where x has been substituted with 0, just becomes 0 equals 0. And 0 equals 0 is a tautology. So that just becomes true. Alright. And so this basically, this Hoare triple becomes, so from the assignment axiom, we've been able to construct the Hoare triple true x colon equals 0, x equals 0. Similarly, from the assignment axiom, we've been able to construct the Hoare triple x equals 0, x colon equals x plus 1, x equals 1. Now I can apply my composition rule. This becomes my P, which is true. X equals 0 becomes my R. The first statement becomes C1. X equals 0 is again R. X equals 1 becomes Q. And this second statement becomes C2. And so this becomes P C1R holds and R C2 Q holds. Then I know that P C1 semicolon C2 Q holds. And so this is coming from the composition rule. So this time I am basically defining the Hoare logic constructively and saying what are the Hoare triples that can be constructed using a set of rules. So far I have introduced 2 rules, and based on those 2 rules I have shown that this Hoare triple can be constructed, and I have also shown a construction procedure for this particular Hoare triple, which involves the instantiation of the assignment axiom and that too twice, and then involves an application of the composition rule, and that's done once. Alright, so we understand what I mean by constructive specification of Hoare logic. Now let's look at another rule, which is the if then else rule, which is the third rule in our set of rules. The rule says if P and B C1Q holds for some predicate P and some Boolean condition B, some program C1 and some predicate Q, and P and not B C2Q holds. So P and the P's are common, the B's are common, and the Q's are also common. The only difference is this time I have C2 instead of C1. Then P, if B, then C1 else C2Q holds. So B is, these 2 B's are, so this B becomes the condition of the if then else. This C1 becomes the then body, and this C2 becomes the else body. So I'm basically saying that if P and B C1Q holds, P and not B, C2Q holds, then P if B1 then C, if B then C1 else C2Q holds. Once again, let's look at an example to understand this in more detail. So let's look at this program. If x is greater than 0, skip, else x colon equals minus x. This is a program that we have seen before, and the Hoare triple here is that we are interested in, let's say, is the precondition is x equals x naught for some, let's say, value x naught, and the post condition is x equals modulus of x naught. It's easy to see that this Hoare triple actually holds, informally speaking, because if x is greater than 0, then nothing happens, and that's basically because x is already positive, so it's going to give you the same answer. But if x is negative, then you negate it to get a positive value, and so at the very end you're going to get x equals modulus of x naught. Alright, so now I'm going to apply my if then else rule to show that this Hoare triple can also be constructed. So to be able to construct this Hoare triple, I need to first construct the corresponding Hoare triples for the then body and the else body. So here I show the Hoare triple that is required for the then body. The then body says x equals x naught, skip x equals mod x naught, but not just x equals x naught, but also I need to do and b, where b here is x greater than 0. So this Hoare triple that I require to be able to construct this larger Hoare triple is that p and b, so p is x equals x naught, that's coming from here, b is x greater than 0, which is coming from here, c1 is skip, which is coming from here, and q is x equals modulus of x naught, which is coming from here. And I want to show that if x equals x naught and x is greater than 0, and I do nothing, so skip is nothing but a no-op, so I can even kind of, although I haven't specified a rule for skip, it's almost like saying that nothing happened, then x equals mod x naught. And it's easy to see that this is true, and we'll use some kind of logic, and I'm using first order logic here, where first order logic I mean that there can be quantifiers on values, but not quantifiers on higher order functions and things like that. So here we have x equals x naught and x greater than 0. Don't do anything, and that means x equals modulus x naught. Can I prove this? I can prove this using first order logic, because x equals x naught and x is greater than 0. So this just basically, because this is a skip operator, I really don't need my constructive rules. I just need to show that this implies this, and that's actually true, because x equals x naught and x is greater than 0. That basically means both x and x naught are positive values. That also basically means that x also equals modulus of x naught. So it's easy to see that if p and b hold, then q holds, because the program is just a no-op, so I don't really need to really construct a Hoare triple. I can just use first order logic to prove this Hoare triple, or this obligation. Now the second proof obligation that I want to prove for constructing this larger Hoare triple is for the else body. And for the else body I say, so first of all, just in more detail, if I'm looking at the then, okay, so when I looked at the then body, then I just had the skip instruction, and we just use first order logic. But when I look at the then else body, then I have this instruction called x colon equals minus x. So that forms my C2, and this time the Hoare triple that I want to construct is P and not B. So not B becomes x is less than equal to 0, I should say. So x is less than equal to 0, and x equals x naught, that's P. Not B is x is less than equal to 0, that's just not of x is greater than 0. C2 is x colon equals minus x, that's the program. And then Q is x equals modulus of x naught. Now I can x equals x naught and x is less than equal to 0 is the C2 x equals modulus of x naught. Can I construct this? It doesn't seem like we can construct this using the rules that we have so far. Let's see what we can construct. What we can construct using the assignment axiom, because there's an assignment statement here, is that if x equals modulus of x naught, that's my P, then if I just substitute minus x for x, then that this Hoare triple holds. So minus x equals modulus of x naught. So just to make this clearer, here I'm just doing P x colon equals e. This thing here, minus x is e, and this is p. All right, and so what I just copied p here, which is x equals modulus x naught, except that I replaced x with e, and e is minus x, so that becomes minus x equals modulus of x naught. So using the assignment axiom, I can construct this Hoare triple, but not this one. But it turns out that these two Hoare triples are actually identical, because if I just apply first order logic, I can show that minus x equals modulus of x naught equals x equals is the same thing as x equals x naught and x is less than or equal to 0. Because minus x equals modulus of x naught basically means that x was negative, because modulus of x naught is definitely positive, and if minus x is a positive number, then x must be a negative number. And also we know that so minus x equals modulus of x naught. Actually, these are not equivalent, but this is more like this should be an implication, because it's possible that x naught was a positive number. So I should have really said these imply here. All right. So I'm saying that if x equals x naught and x is less than or equal to 0, then minus x equals modulus of x naught, but not the other way around. And so this is a problem. I mean, from the assignment axiom, I was only able to construct this Hoare triple, but what I really require is this Hoare triple. And so far I don't know of a way of constructing this Hoare triple, because I wasn't able to construct one of the smaller Hoare triples. In particular, I wasn't able to construct the Hoare triple that was required for the else clause, which is this Hoare triple. What I was able to construct was this Hoare triple. And these two Hoare triples are actually not equivalent. So I think I said they are equivalent in the just now, but they are actually not equivalent, because this the precondition of this Hoare triple is different from the precondition of this Hoare triple. The precondition of this Hoare triple is actually stronger than the precondition of this Hoare triple, and it is easy to see that if this holds, this Hoare triple holds, and this will also hold. But so far we haven't discussed the rule which says that, and so far we won't be able to construct this Hoare triple as such, and so this Hoare triple cannot be constructed by the three rules that we have discussed so far. I'm going to discuss a fourth rule very soon that's going to allow us to reason about, to be able to construct this Hoare triple as well. Similarly, here again, if I just kind of made the condition stronger and said x equals x naught and y equals 1 for some variable y, and this is the Hoare triple that I want to prove. Now it's easy to see that this Hoare triple is also true, because I've only made the precondition stronger. I've added more constraints on y, but it's not possible to prove it, because I'm not able to construct this Hoare triple. What I'm able to construct is this. So I'm able to construct this Hoare triple. I construct this, but I require this, and so I am stuck. And so basically that means that so far the three rules that we have discussed are insufficient to be able to construct this Hoare triple. So to be able to solve this problem, there is a fourth rule in the Hoare logic that I'm introducing, which is that if P implies P prime for some predicates P and P prime, and P prime C Q prime holds, and Q prime implies Q for some Q prime and Q. So notice that the Hoare triple that holds is P prime Q C prime, but then there are extra predicates P where P is stronger than P prime, because P implies P prime, and Q is weaker than Q prime because Q prime implies Q. Then it also implies that P C Q holds. And this is called the consequence rule, and this is going to be a very important rule as we go along. And basically it kind of says that if a stronger post precondition implies a post condition, if a precondition implies a post condition, then a stronger precondition will also imply a weaker post condition. So if P prime C Q prime holds, then a stronger post precondition P C weaker post condition Q also holds. And to see this with an example, in this particular example, we were able to construct minus x equals modulus of x naught, x colon equals minus x, x equals modulus of x naught. Now let's assume that this is P prime, minus x equals modulus of x naught. This is Q prime, x equals modulus of x naught. And now let's look at this particular statement here. let's say this is P, and now this is Q. Now it's clear that Q prime implies Q, because Q prime is X equals modulus of X naught, so Q prime implies Q. P implies P prime, so you can see that's going to come from first order logic. If X equals X naught and X is less than 0 and Y is equal to 1, then that means that minus X equals modulus of X naught. It's easy to see that P implies P prime. Then we can show that P C2Q also holds. And because we have been able to show that P C2Q holds, earlier we had shown that P C1Q holds. From that we are able to show that P if B, we have been able to show P and not B C2Q holds, to be more precise. Earlier we had shown that P and B C1Q holds. From that we are able to show that P if B C1 else C2Q holds. So this way we have been using the 4 rules. The consequence rules was important here. Using the 4 rules, assignment axiom, composition rule. Actually in this example we didn't really use the composition rule. In this example, we used the assignment axiom, the if then else rule, and the consequence rule to be able to construct this particular Hoare triple. So, in general, identifying the required P prime and Q prime is the key. And we have seen earlier that for acyclic code, we can find pre-images. For example, we can just say, okay, if this is Q, then I just find what is the corresponding pre-image here, which is just, substitute E for X in Q, and that's the pre-image of Q here, and so on. And using that, we are able to find what P prime and Q prime should be. In fact, here also P prime just came from that, because we just took the pre-image of Q, which was X equals modulus of X naught, and took its kind of pre-image across this assignment statement, and that became a P prime. And then we just had to show that P implies P prime and Q prime implies Q. And so in this particular example of if then else, which actually represents an acyclic program, it's possible to always find these P prime and Q prime through this pre-image mechanism. But in general, this is going to become harder in the presence of loops, as we're going to discuss later.